Okay, hello everyone. This is one of the pedagogical introductory lectures for Dark Energy from Home 2026. My name is Tessa Baker. I'm a professor at the Institute of Cosmology and Gravitation at the University of Portsmouth in the UK. And I'm going to be telling you about one of the major areas of my work, which is how we use gravitational wave observations as probes of dark energy. What can we learn from that data? So we'll do this in sort of three sections today. First of all, we'll revisit gravitational wave propagation. Firstly, just in general relativity, and then we'll show how that propagation changes when we look at theories of gravity beyond general relativity. And on my slides today, mg will stand for modified gravity. And what we'll see in that propagation study is that there are two sort of dominant ways in which dark energy or modified gravity, I'll use those terms interchangeably, can affect gravitational wave propagation, which are the propagation speed and the gravitational wave luminosity distance. And so in sections 2 and 3, we'll break down each of those observables a bit more and look at the current constraints. And I'll briefly mention that this lecture I'm giving here is a sort of one section of a series of lectures, effectively, that I gave at the 2025 Michigan Cosmology Summer School. So if this kind of topic is of interest to you, or you want to find out more about some of the tests of Horndeski gravity that we'll talk about shortly, there's a link on the slide to the YouTube channel of that summer school where you can find all my lectures. Okay, so let's get started by looking at gravitational wave propagation in GR and beyond. And just as a sort of brief, caveat to what we're going to talk about today, I will be focusing almost exclusively on gravitational wave propagation and not generation. So gravitational waves themselves are sort of probes of two very different regimes of gravity. So of course they're generated in a strong field environment near a compact object binary, and there could be deviations from GR in that regime. But then when they leave that binary, they exit the host galaxy, they travel across the large scale structure of the universe, and they might be sensitive there to any cosmological scale departures from general relativity. So the strong field regime is really what I'll call the generation of gravitational waves, and the weak field regime that we'll talk about today is the propagation regime. And of course, there's lots of work on testing gravity in the strong field regime. That's just a separate talk. Okay, and that's effectively what I just said in words. Okay, so to talk about propagation, briefly, I just wanted to sort of remind you how we get to the propagation equation of a gravitational wave. So this is a little bit of a sort of GR recap done, without fussing too much over all the factors of 2 and pi and things. So what we'll do is we'll take our space-time metric of general relativity, g mu nu, and we'll write that as some background metric, which we'll call eta, and a small perturbation on top of that, which we'll call h. And schematically, I'm indicating that all the components of this h perturbation are small relative to the background eta. And we take this sort of split of the metric and we plug that into our standard computation of the Einstein tensor, capital G mu nu, which of course is the thing that sits on the left-hand side of the Einstein field equations, shown here with a c set to 1. Okay, so when we do that, what we get is the thing I'm showing on the slide here. So this left-hand side becomes a box operator, right? So that's contraction of time-like and space-like second-order derivatives acting on an object I've called h bar, which is a little bit of a compact way of writing this combination of the metric perturbations, sometimes called the trace-reversed perturbation. And of course, on the right-hand side, we've got the stress energy tensor that tells us about the content of space-time. But if we're in that large scale structure regime outside the host galaxy, for most of that intergalactic space, the space is empty, right? So we'll set that stress energy tensor to 0. And then what we have is this propagation equation that it's effectively box H equals 0. That's our starting point. Now, if we make some particular choices of the gauge, which I won't go into today, then we can write things in a very simple but kind of illuminating form. So this is for a gravitational wave traveling along the x-axis, and this TT on the left-hand side here indicates I've made particular gauge choices. But for this gravitational wave and this gauge choice, we can solve the equations and find out that there are only 2 real degrees of freedom here, which are given by these components plus sitting on the diagonal and cross on the off diagonals. So there's really only 2 modes here which describe the 2 polarizations of a gravitational wave in general relativity. Okay, so what we're going to do is we're going to pick apart a little bit more this box H equals 0 equation in a cosmological setting. Okay, so here we go, and I'm playing a bit fast and loose with indicating the gauge choices and things like that. So on an FRW background, so a smooth expanding background, if you expand out this box H equation, it becomes what I've written on the slide here, where primes are indicating derivatives with respect to conformal time, and so the curly H in here is the conformal Hubble factor. And what I've done, I'll just go back a little bit there. So we've got a second order time derivative. We've got a kind of friction term here with a first order time derivative. And we have a second order spatial derivative. But I will go to Fourier space where that nabla squared will become a factor of plus k squared. Okay. So as we've said already, kind of packed in here, and I'm now explicitly writing the spatial components, packed in this Hij are the plus and cross polarization modes. We won't really project them out today. And we've said already there's this kind of Hubble friction term. So this is the situation in general relativity. And what we want to ask for our purposes is how does this propagation equation change in modified theories of gravity or dark energy theories? So I'm going to show you a kind of template equation, if you like, for what changes can come in here. Okay. So here we go. So stuff's moved around a little bit, and all the new things that I've added have been written in color to help you kind of pick them out. So I stress, I haven't derived this for you today. This is not a particular modified gravity theory. This is just a kind of phenomenological sort of template equation showing you which parts can be changed. So first of all, this friction term has picked up this extra object. I've just called it nu for now. I've indicated it can be a function of redshift. And so we'll call this our modified friction term. And your intuition might say if you change the friction of a wave, that's going to affect how it damps, how it drops off as it travels. So that's going to affect the amplitude. And indeed, we'll come back to that a little bit later. This term here is the propagation speed of the gravitational wave. So on the previous slides, of course, it was c, the speed of light, and I think I probably had that in units where c was equal to 1, but this can be different from the speed of light in modified gravity. This term here is indicating an extra term that appears if we have a massive graviton. Of course, the graviton in general relativity is massless. And then on the right-hand side here, I've got a source term. So remember in GR, the right-hand side was 0. That tells us gravitational waves are unsourced once they've left their sort of compact binary where they're produced. So they travel across the universe. Nothing is kind of coupling to them or sourcing them. But we've allowed for that to be not true in our modified gravity theory. This object gamma here is just really there to preserve the sort of tensorial nature of the equation. And there's a final way of changing this equation, which as I sort of indicated, I'm not going to delve into the details of now. But in general relativity, we saw that there were only those two polarization modes, whereas in extended theories of gravity, you can have more polarization modes. Essentially, you can have extra scalar modes, extra vector modes, etc., beyond the usual plus and cross. Okay, so as I said, this is just a kind of general zoo of phenomenology, and we do know of particular modified gravity theories that give rise to each of these terms. But what I am going to do today is I am going to focus specifically on one family of modified gravity theories that really sort of dominates a lot of the current literature. And that's Horndeski gravity. So this might have come up in some other talks already for this conference, but I will just sort of briefly revise what this is. So Horndeski gravity is a family of gravity theories, really. And it is the family, if you like, the most general action, in formal words, that contains a metric like general relativity does, and one extra scalar field. So it's the family of what we call scalar-tensor theories, because there's a tensor and there's a scalar. And the Horndeski action is quite big. I am going to show it to you today because it's going to be kind of important in some of the calculations I want to walk you through. So we sort of write it in this form. So of course it's an integral with its usual space-time element. And it's written as a stack of four Lagrangians, and then this last term is just indicating that there's matter present. And I'm not going to delve into non-minimal matter couplings today. So the first piece of the action is L2, which is, if you like, the generalization of the kinetic term of your scalar field, which you would write down when you write down any scalar field theory. So for now, we're just going to leave this as a function k for kinetic, which is going to be a function of our new scalar field phi. And this object x, which is going to appear a lot today, I've written it in the top right-hand corner. X is just the standard canonical kinetic term of the scalar field. So nabla phi, up to a factor of a half. But in our modified gravity theories, that could be generalized to something more complicated. So L3 is then another piece that I'm going to write as another function. We'll call it G3, function of phi and x, which multiplies box phi. And this is the term we're allowed to write down. We can have any functional form for G3, just as we can for K. And this term is particularly important because this box phi gives rise to a kind of screening mechanism known as Weinstein screening. And in one line, screening, which is a whole topic in its own right, is a set of mechanisms by which the effects of modified gravity can be kind of hidden in certain environments. So you don't break, for example, the fact that general relativity holds really well in the solar system. Then things are starting to get longer and longer. So L4, the third part of the Lagrangian, looks like this. So it's got another function of phi and x, which we'll call G4, multiplying the Ricci scalar. So notice that the GR limit of the theory lives in here, right? If we set K to 0, G3 to 0, and we set this G4 to be equal to the Planck mass squared over 2, we'd get back general relativity. And then there's a rather complicated term here involving a derivative of G4. And the last part, I promise, so L5 is the quintic part of the Lagrangian. As you can see, stuff is getting longer and longer. So again, it's characterized by a function of phi and x. And this essentially just holds all the remaining terms you can write down for this scalar tensor theory, which will not give you equations of motion that are greater than second order in derivatives. And that's really important for the stability of the theory. So the top line is that there's four functions here, k, g3, g4, and g5, which specify a scalar tensor theory. And this is what I said already, that's how you recover GR from this action. Okay, so this is Horndeski gravity. Now I'm going to show you how this changes the propagation equation. And the link's not going to be completely obvious right now. I'm going to slightly sort of change the mathematics, but we will come back to this Lagrangian later in the talk, which is why I wanted to show it to you now. So if we take this general Lagrangian, and we ask, what does it do to this modified propagation equation we had before? I can tell you it will only activate two of these terms. And it's these two in the middle here. So in Horndeski gravity, you can have this modified friction term and you can have this modified propagation speed. And all the other terms are not present in this family of theories that we're going to study. So the friction term here, which I wrote as sort of nu of z, that actually comes from that G4 function, which was the one that sort of multiplied the Ricci scalar, was holding the standard GR limit. And essentially this object is non-zero if G4 is evolving, if it's a function of time, which is why, of course, in general relativity, when it's a constant, nu is zero. And so we'll call this object, at risk of sort of changing notation a bit, we'll call this alpha m, because that's one of the standard bits of nomenclature that's used in the literature. I'm not sure I've got the reference here, but it's Bellini and Sawicki 2013, I believe, introduced this alpha m object. Which describes effectively the running of this G4 function, which acts like an effective Planck mass. And then the other parameter we're going to focus on a lot. So when we change that propagation speed, ct, we often write ct squared is equal to 1, it's the speed of light in our units, plus this factor alpha t. So again, if alpha t is 0, we've got general relativity, gravitational waves travel at the speed of light. But in our Horndeski theories, that doesn't have to be the case. So essentially that big action for Horndeski theory boils down, at least as far as gravitational wave science goes, to two objects, alpha m and alpha t, that are both functions of redshift, and these are things we want to constrain with the data. So section 2, we've derived that propagation equation in Horndeski gravity. Let's now talk about constraints on that propagation speed term, which is going to be characterized by this object alpha t, which is 0 in general relativity, and of course can be a function of redshift in modified theories of gravity. Okay, so there are some very strong constraints that have already happened on alpha t, the deviation of the propagation speed, coming from the binary neutron star merger GW 170817, which of course happened in 2017. And as I think many people will know, this is the only gravitational wave event that has happened to date that has been a bright siren, meaning that we have detected both the gravitational wave and the electromagnetic counterparts of the event. So the event was, of course, seen across the electromagnetic spectrum, but for our purposes today, the key point is the gamma ray burst, which is the first photons to be released from the merging neutron stars. So my highly accurate, definitely not to scale diagram here, we've got the host galaxy, which is NGC 4993. That is the actual host galaxy in the background there, though it's a bit obscured. And we've got our neutron stars here merging. And of course, our gravitational wave signals and our GRB photons, both traveling towards our telescopes and our gravitational wave detectors on Earth. And famously, these signals arrived 1.74 seconds apart, with the gravitational wave signal arriving first. Now, of course, that's not quite true because the gravitational waves is a waveform, right? But what I mean by that is the peak of the signal, the kind of moment of merger, that reached Earth 1.74 seconds before the first GRB photon was detected. And so the fact that there is this sort of time delay measurement that acts like a race, if you like, between these two signals, and we can use that number to place a bound on their relative difference in speed between speed of light and gravitational waves. So here is what was actually detected in slightly more scientific format than my diagram. So at the top and bottom panels here, you've got gamma ray flux counts in the Fermi and integral detectors. And the green line here is indicating the start of that gamma ray burst. And in the middle panel here, you've got a spectrogram from one of the gravitational wave detectors that was operating at the time, and you can very clearly see by eye that chirp signal, and you can literally see on this plot that the gap is less than 2 seconds. So what we're going to do is a sort of a quick calculation to compute this speed bound. And the version I'm going to do on the slides is slightly naive because it uses like Newtonian physics instead of actual cosmological distances. But because this event was so nearby the Earth, it was only about 40 megaparsecs away. It's, you know, not that far away from our own galaxy. Actually turns out that the Newtonian calculation gets very close to the full result. This difference in arrival times between our photons, which we'll indicate with a gamma, and GW, the arrival time of the gravitational waves. Newtonian physics, time is distance over speed, right? So the distance to this object, and of course Newtonian physics doesn't know about things like conformal distances or luminosity distances. It's just got one notion of distance. So distance divided by speed for both the light and the gravitational waves, easy. So we're just going to pull out a factor of d over c gamma like that. And then to make life super easy, of course, I'll set c gamma, the speed of light, to be 1. We'll bring it back when we need it for dimensions. I'm also going to plug in that ct squared in our sort of Horndeski notation is 1 plus that deviation alpha t that we want to constrain. So we'll take a square root and plug this in. Okay, there we go. Now, we are going to make the assumption that alpha t is very small compared to 1, and this will turn out to be a very good assumption, which means we can Taylor expand that denominator. So just doing that Taylor expansion to bring this up to the top, we get the following, and you can see immediately that the 1s are going to cancel, and just doing a bit of rearrangement of delta t d alpha t, just rearranging that expression gets us to this down the bottom here. And I've brought the factor of c gamma back in just to show you that dimensions work. And so the distance to the host galaxy, we know later on from the kilonova and identifying the host and studying it spectroscopically, is about 40 megaparsecs. And that difference in arrival time we said was 2 seconds or less. And so plugging in those numbers, you find that this alpha t on the left-hand side has an order of magnitude that is around 10 to the minus 15. Okay, so it's way, way smaller than the number 1. So any deviation of the speed of propagation of gravitational waves from the speed of light is at most this order of magnitude, which is very, very small. And quite possibly it's actually 0. The reason this computation doesn't return 0 and the two signals do arrive with a slight delay is quite possibly because there's actually a delay at the merger. So the binary neutron stars merge, the gravitational wave merger signal is released, but it actually probably takes a couple of seconds for gamma ray photons to be produced by the various processes, and also to punch their way out through the very dense remnant of what's going on. So most likely the standard explanation would be that small difference, which is what leads to this kind of residual deviation from the speed of light here, is purely astrophysics, and really the speed of gravitational waves is the speed of light. That's the standard interpretation. If you want to kind of pick holes in that, you can point out that this is only one measurement. And as I've said, this event was very nearby in terms of redshift. It was about redshift 0.01. So we've only got a data point here that in principle doesn't rule out there being more exotic physics that might be changing the speed of gravitational waves at higher redshifts. Now, there have been some studies done using dark science techniques that we'll get onto later in this talk, and so far no one's found any evidence of any funky stuff happening at higher redshift. But it's important to say this uber tight bound does just come from this one low redshift data point. So I've bounded this number alpha t, but what does that actually imply in terms of the original actions of gravity we were looking at? So I introduced in part one the Horndeski Lagrangian, which was made up of this whole stack of terms. So what I want to do is walk you through the interpretation of what this means if gravitational waves travel at the speed of light. Okay, so here we go. So I haven't shown you this computation before. You can find it in some of the papers that are actually referenced on earlier slides. But this alpha t function is related to these objects appearing in the Horndeski Lagrangian as shown here. Okay, I'm sorry, my colouring here is a bit inconsistent. That should have also been purple. So it's this combination of a bunch of factors we don't really have to worry about and a square bracket containing these three derivatives, the derivative of g4 with respect to x, the derivative of g5 with respect to phi, and the derivative of g5 with respect to x again. And barring any kind of magic cancellations between these objects, which would be very fine-tuned and very hard to preserve, the easiest way to get alpha t to be approximately zero, right, because it is approximately zero with our really tight bound, is to say that each of these derivatives individually has to be equal to zero. Okay. So if all of these three things are equal to zero, what does this imply for the Lagrangian above? So let's take this one first. If g5 comma x, meaning derivative of g5 with respect to x, is equal to zero, what happens? Well, that whole bottom term disappears, right? That had a, sorry, playing around, but just to help you see, that had a derivative here with respect to x. So that's gone. We've still got this piece left here, but we're also setting the derivative of g5 with respect to phi to be zero. So what that means is this object g5 can at most be a constant. And then because all of this term is sitting in an integral, you can do an integration by parts. What will happen is that one of these nablers, one of these derivatives, will come over here, it will pass through the constant, it will hit the Einstein tensor, and the derivative of the Einstein tensor is zero by the Bianchi identity. So actually we lose all of that L5 term. One more piece to go. We know that the derivative of g4 with respect to x must be zero. Note that that appears here. So we're going to lose all of this term. And finally, if g4 can't depend on x, then it can only depend on phi. So we're going to just simplify this dependence here. So at the end of the day, we're left with just these three very short Lagrangians compared to what we had written down originally. This is the limit of the Horndeski scalar tensor family that will give luminal gravitational waves, meaning gravitational waves that travel at the speed of light. So here's the remainder. I've just sort of written them out a bit differently. You might think that this rules out most of the modified gravity model space. And that's actually not true. It did rule out quite a few theories, but of course these are functions, which means that there's kind of an infinite number of things you could put in place of K, G3 and G4 to get a new gravity theory. And just to give you one really well-known example, you might have heard of F of R gravity. That's a particularly well-studied theory that fits in this reduced template, as I'm showing here. It just uses G4 and K, it doesn't use G3. And so F of R gravity has luminal gravitational waves, and so it survives this bound. Okay, and there's many other examples I won't run through today, things like quintessence, K-essence, cubic Galileons, etc., that all fit within this template. Okay, here we are now on the third section of the talk. So having looked at the propagation equation, having seen that the propagation speed is already tightly constrained, we'll move to the second major sort of change, which was the effects on the gravitational wave luminosity distance. And this is all going to center around constraining this other Horndeski function, alpha m. So just to remind you where this fits in, here was our propagation equation in Horndeski gravity. And as we've said, propagation speed seems to be very, very close to the speed of light, so we'll set that equal to 1. And that leaves us to focus on this modified friction term. So what does this friction term do to a traveling gravitational wave? Well, again, we can do a kind of simple calculation to tease out the physics of that. So here's what we're going to do. We're going to do a sort of ansatz solution. So we're going to say, let this gravitational wave h, and we're going to drop the indices and just not worry about the sort of tensorial nature of this for now. Let h be equal to its GR value, whatever that is, multiplied by this factor here. So we're going to allow for a change to the amplitude of the wave, which we'll call B, and then also a change to the phase of the wave, which is sitting in our exponential here with the imaginary argument. So the phase change will be C. And we plug this solution into this equation and solve. And so what actually happens when we plug this in, of course, is we get an equation with real and imaginary parts because of the derivatives. And so we can separate the real and imaginary parts, two equations, two unknowns, B and C. We solve for them. And what we find is that C is 0. So there's no phase shift induced by this modified friction term. However, the solution for B, the amplitude change, is more complex. Not literally complex. It's real, but it's complicated. So B can be written in the following form. So it's an exponential, and the arguments of that exponential have this integral over alpha m, integral in z with some factor of 1 plus z on the denominator. So somehow the amplitude of the wave is sensitive to the behavior of alpha m all the way between the source and the observer, right? Which kind of makes sense. Okay, so I'm just going to move that solution up just so we can see it. Now let's ask what this actually does to our gravitational wave signal. So I've written on the slide here an expression for the amplitude of a gravitational wave in general relativity at lowest Pn order, and also for the simplest system I could think of. So it's a pair of non-spinning binary black holes on a circular orbit. And so what does this depend on? So this depends on this object in the denominator, which is the luminosity distance in general relativity. There's the chirp mass, more specifically the redshifted chirp mass, which we'll come back to shortly. And then there's some frequency dependence, and then there's a load of angular parts to do with the polarization and the inclination of the system. What we really care about today is this object in the denominator. And what's going to happen when we multiply through this factor B is it's effectively going to be absorbed into a change in this distance here. So now I've written this as dGW, the gravitational wave distance, rather than the standard luminosity distance. Okay, you can't distinguish between a change in distance and a change induced by this new modified gravity factor. So what we have is that this new effective distance that appears in our waveform is the standard luminosity distance. That's what it would be equal to in general relativity, but now with this additional factor multiplied into it. Of course, the source hasn't actually moved. It's in the same place. No real distances have changed, but the number that you measure from a waveform and interpret as a distance is no longer a distance. It's this modified distance. So we can think about the ratio of this new luminosity distance, the gravitational wave luminosity distance, to the standard luminosity distance, right? And as we've said, in GR, those things are equal, so the ratio is 1. And again, we've got a situation here where a deviation from 1 indicates the behavior of a modified gravity theory. Okay. So what we will do generally to help us make progress here is to plug in a particular form for this function alpha m. So in a particular modified gravity theory, a particular realization of the Horndeski family, you could compute what alpha m is exactly. But when we want to be a bit more model independent than that, it's very common to make an ansatz of the form shown on the slide here. So here Cm is just a constant, and that's going to be the constant we're going to try and constrain. And then the rest of this function is omega lambda as a function of redshift divided by its value at redshift 0. And this is just an object which is 0 at high redshifts in the early universe and tends to 1 at late times in the late universe. And what we're doing here is we're just baking in a sort of assumption that modified gravity or dark energy are late universe effects. We generally don't want to go and modify the matter-dominated era, for example, because that breaks a lot of structure formation. So we are imprinting a sort of extra layer of modelling on the theory here. But with that in hand, and that's a very common assumption, we can ask them, what is the behaviour of this luminosity distance ratio? And I've got a plot here just showing some sort of toy model examples of that for different values of this CM parameter. Okay, and it could be positive or negative. And so the flat line here in grey is GR, where things are 1. And this blue and this red curve indicate these modified gravity models. And overlaid on this plot, there's a sample of mock data points, so these aren't real, just indicating sort of mock LIGO-like events, or really LVK-like events, current gravitational wave detections, and also some high redshift detections from LISA. Okay. But what you really need to see is that these curves start very close together and then they break apart, they deviate at high redshift. So the departure from general relativity is strongest at high redshift. Now, let's ask if we can go about constraining this parameter Cm. And the first thing that might come to your mind is to use the bright siren 170817, just as we did for the propagation speed. And at first glance, why not? Right, we've said this object on the numerator is something we measure from the gravitational waveform. This object on the denominator, the normal canonical luminosity distance, well, that's given by the expression here. And if we know the redshift of our gravitational wave source, which of course for the bright siren we do because we see the host galaxy, we can get the redshift of the host galaxy, we can compute this formula here for some cosmological model and we can get the denominator. So why not go compute this ratio and use it to constrain alpha m or Cm? And so people tried to do this. Okay, and what happens is that the constraint turns out to be very weak. So I'm showing a plot here, which is from Lagos et al. 2018. So this was the year after the bright siren. You're seeing marginalized 1D posteriors constraining this Cm parameter from our ansatz. Now there are two curves because there are different priors used for the Hubble constant. Right, because the Hubble constant features in here in the normal luminosity distance, and so it does impact the constraints. But nevertheless, both the blue and the green curves have roughly a sort of 2 sigma bound that's of order about 60 or 70, right? Well, 60 or 70 on the negative side, maybe about 40, 45 on the positive side. So this is a really weak bound. Right, compared to alpha t that was constrained to 10 to the minus 15, we've constrained alpha m to kind of order plus or minus 50. Right, that's huge. That doesn't rule out really many theories at all. So why is this so weak? And the answer is because 170817 was at such low redshift. Remember on this plot, the departures from GR are tiny there, so it's not got a good hold on them. And of course, as we said, you really want to go testing gravity out at high redshifts. So this is a point that's kind of contra to perhaps the usual story of gravitational wave cosmology, where all of our constraints are better with nearby events. If you want to constrain the Hubble constant, you do best with nearby loud events. But actually, if you want to test dark energy, you do better with events at high redshift, as long as they're sufficiently loud and sufficiently well localized. So we need some other method. And we need events at higher redshift. Now, luckily, there are many such events. This is a plot from the third observing run of the LVK detectors. So this is quite out of date now. I should update it with one from the fourth observing run. But this is just to show you that many of the binary black holes that LVK detects go out to redshifts centering around nearly 1. So we've got these events at high redshift. The problem is that, of course, they don't have electromagnetic counterparts. They're just binary black hole signals. And that means that we don't get any redshift measurement for them. So we can measure the denominator from the waveform, but we don't have a sort of super precise way to get the, we can measure the numerator, we don't have a super precise way to get hold of the denominator. However, there is a sort of major method that has been developed to do cosmology with this kind of data. And that goes by the name of dark sirens, which of course is opposite to bright sirens. So we can obtain some information on the redshift of a gravitational wave event, even when it doesn't have an electromagnetic counterpart. And it's going to be less direct, less precise, more statistical, but we can do it. Now, in the interest of time today, I'm not going to go through the sort of whole Bayesian formalism that sets up this computation, but you can find that in a very nice sort of pedagogical paper that I've linked at the top there. But sort of qualitatively, where this redshift information comes from is 2 places. First of all, it comes from features in the mass distribution of compact objects. So here is the latest plot from actually the first part of the fourth observing run of LVK. And what you're seeing here is how common is it to have black holes at particular masses, okay, for the primary of the binary. And you can sort of forget about the blue and the black dashed here. Really, the orange is the main result. And you can see there are these peaks, right? So the location of these peaks is something we have to determine. It's not known, so we'll give it some parameters, mu1 and mu2. There's some power law slopes going on here, alpha1 and alpha2. But the key point where this gets entangled with cosmology is that these masses that are appearing here are source frame masses, right? Whereas what we actually measure from a waveform are redshifted masses. So curly M here is the chirp mass. We measure the thing on the left and we try and infer the thing on the right. But there sits here this factor of redshift, which is connected to the Hubble constant. So actually, if we increase or decrease the Hubble constant, what we do is we push the positions of these features up or down in this kind of mass space. So we get some extra information on the redshift locations, if you like, of sources from where they are most likely to be put on this mass spectrum. We're more likely to get events around where these peaks are. And that's all worked out statistically in this dark sirens formalism. So that's one piece of information. The second piece of information is that we are able to derive a prior on where we think the event is likely to be in redshift space from a galaxy catalogue. So our hypothesis is that gravitational wave events live inside galaxies. And so if you see galaxies, those are potential hosts. So we're going to write down this object P of Z given lambda, where lambda is just indicating your cosmological parameters. But actually this redshift prior, so this thing that would be a kind of delta function for the bright siren and is more generally going to become this complicated distribution. It's going to contain 2 parts. So there's an in-catalogue part for all the events we've seen, and there's also an out-of-catalogue part for all the events that we didn't see. And we have to model both of those very carefully. So I've got some very sort of silly sketches here. I'll show you the real thing in a minute. But basically the in-catalogue part is going to be a very sharply peaked distribution from where we see galaxies and where we see voids. And we have to make some assumption about the galaxies that we didn't see. And the simplest, least biased thing is to assume they're homogeneous in co-moving volume. And just to flash up the real thing, so you see something beyond my kind of sketches, this is a real example of what one of these line of sight redshift priors looks like. So folding together these 2 bits of information on where the source is likely to be in redshift space, we can do this dark sirens analysis. And actually, we have to simultaneously infer the modified gravity parameters that we're actually chasing, but also parameters like the Hubble constant, maybe things like omega matter, either we infer it or we put a prior on it, which appear in the electromagnetic luminosity distance, the parameters that describe that mass distribution, and also parameters that describe the merger rate of compact objects. And this is going to be important for the next slide. So at low redshifts, we can parameterize the merger rate of compact objects in redshift space, as the form shown here with this power law index gamma. And what we find when we actually do the dark science analysis is that our modified gravity parameter that we're trying to measure is degenerate with that gamma index. So here's the headline result from the O4A cosmology paper of the LBK collaboration, which is something I worked on. And so this CM, which remember was our sort of ansatz parameter, you can see constraint here, but you can also see it's degenerate with that gamma. And the blue and the orange here are just indicating different prior choices on the Hubble constant. But the headline result, marginalizing over H0 and all the other parameters, is that CM is constrained to be 0.3 plus or minus roughly 1 and a bit. And so that is a much, much better constraint, much tighter than the kind of plus or minus 50 we had from the bright siren. So the dark sirens method is one of the major ways that we are pushing forward constraints on this remaining gravitational wave friction term. Okay, and that's the end of what I was going to say today. I hope this has been a kind of useful review or whistle-stop tour. The quick summary is that mainstream scalar-tensor gravity theories like Horndeski gravity modify gravitational wave propagation speed and luminosity distance. The propagation speed has been very tightly constrained by binary neutron star merger 170817, and we saw how that kind of rules out the more complex sectors of the Horndeski gravity space. However, the luminosity distances remain open. They are a current sort of major target for ongoing LBK analysis via the dark science methods. And I'll just kind of indicate that there are other methods like gravitational wave galaxy cross correlation that I didn't get around to talking about today. And of course, plenty of details and plenty of frontiers here that are moving forward. All right, thank you very much for listening, and I'll see you at the conference.